Hello and welcome to the video lecture series brought to you by St. Andrews Institute of Technology and Management. My name is Ravinder. I am an assistant professor with ETC department, and in this video lecture series we are discussing the subject called Data Structures 2 or Advanced Data Structures. And today we are going to see the last topic the of the unit called graphs that we are discussing for a while now. That is the Warshall's algorithm. Okay, so let's move on to Warshall's algorithm. Now, the Floyd-Warshall algorithm, sometimes called Floyd-Warshall algorithm, is an algorithm for finding the shortest path between all the pairs of vertices in a weighted graph. This algorithm works for both directed and undirected weighted graphs, but it does not work with the graphs with negative cycles. We don't have to bother about negative cycles as we haven't seen that. I think that is out of the scope of your syllabus also, so don't dwell on that. So Warshall algorithm is just another algorithm. We have seen many of them until now, like the Zastra's algorithm in topological sorting, to sort out or to find the shortest path from getting one vertex to the another vertex. In different types of graphs, some of them are weighted, some of them are not non-weighted, some of them are directed, some of them are non-directed. Okay, so Warshall algorithms is specifically designed for weighted graphs, and the graph may be directed or undirected. It doesn't make any difference, as you will see in a short while what I'm trying to say. So this algorithm is basically dependent upon the dynamic programming approach to find the shortest path. That is, you have to remember what you have done in the past. Dynamic programming to actually remembers the past actions and try to use them as frequently as possible instead of doing the same work again and again. So let's move ahead. Suppose we are given that this particular directed weighted graph. Okay, we have four vertices, 1 2 3 4, and the respective edges. So if we have to find out the adjacency matrix of this particular graph, then it's going to come out something like this. Okay, now as you can see that some of the entries inside the graph are sorry, are termed as infinite. The infinity actually tells us that there is no valid edge in that is connecting the two vertices. Okay, so let's read out the first few lines and then we'll see firsthand what I'm trying to say here. So following are the steps given below to find the shortest path between all the pairs of vertices. Now we have to create a matrix A1 of dimension n cross n, where n would be the number of vertices, where n is the number of vertices. Okay, the row and the column are indexed as I and j, as we have done doing that for past few lectures. And for each cell aij is filled with the distance from ith vertex to the jth vertex. If there is no path from ith vertex to jth vertex, the cell is left as infinite. Okay, so let's try to see what I'm trying to say here. Okay, now as you can see, if we go from first vertex to second vertex, that is first to second, the weight is from first to second, the weight assigned to the edge, that is coming from 1 towards 2, is actually 3. So I have marked this particular entry in the adjacency matrix as third. Now if I want to move from vertex 1 to vertex third, so I have to look up edge from vertex 1 to vertex third. There is no direct edge. Okay, neither coming in nor coming out of 1 towards third. So I have marked this particular entry as infinite. And as you can see, all the diagonal elements of this adjacency matrix is 0, because going from 1 to 1 will always be equal to 0 because we are already there. So going from 2 to 2 is 0, going from third to third is 0, going from fourth to fourth is 0. Okay, Let's take one more example. Say I have to move from the second vertex to fourth vertex, so I have to look for a direct edge. Yes, there is a valid edge which has been weighted as 4. So from moving second vertex to fourth vertex, the weight that has been associated with the edge is actually 4. Okay, so this is how we have made the matrix A naught. So let's move ahead towards the nodes. Let's see what would be the next step. So I've already made this adjacency matrix. Now second step will be to modify this matrix by taking one of the edges, sorry, by taking one of the vertices as the middle vertex from getting one vertex to some other vertex. Okay, let me say that again. We have to make an make an adjacency matrix or modify our A naught matrix, this which is this that we have just derived that from the graph, such that we have to take one vertex as the middle vertex, and that middle vertex must be the vertex which you have to cross from getting, let's say, vertex x to vertex y. And if I say that vertex k is the middle one, so getting from x to y via k, that k must be there. So let's read out what I am trying to say, and then we'll see firsthand what is actually happening. Now to create a matrix A1 using matrix A naught, the elements in the first column and first row are left as they are. That means if I am computing A1, now A1 states for that I am fixing the vertex 1 as the middle vertex. So in that case, first row and first column will be fixed. Okay, and all the diagonal elements will remain 0 as before. But and rest of the entries we have to find out. And what is the rule to find out those entries? We'll just see in a minute. Okay. Now let k be the intermediate vertex in the shortest path from source to destination. Source may be, let's say, node vertex number 2, and destination may be, let's say, vertex number 4. So from getting to from vertex number 2 to vertex number 4, if there is a path which leads from vertex number 1, which we have fixed as intermediate vertex, so we are getting like from 2 to 1 and then to 4. Okay, so in that case, if the cost or the weight of getting from I to the source to intermediate matrix plus from intermediate from intermediate vertex to destination, we have to calculate that first. And if getting from source to destination, that is the weight of the edge from getting source to destination, is more than the total cost or weight getting from source to intermediate plus intermediate to destination, in that case we will replace this with this quantity. Yeah. Okay, so you can see that we have done this before. Actually, we have done this in the Jastra's algorithm, where from getting from node 1 to node 3rd is either I can directly go from node number 1 to node number 3rd, which has a weight of 80, or I can go from node number 1 to 2 first and then 2 to 3rd, which only cost me around 16 distance. Okay, or the distance is 16 only in that case. So this is the same condition here. So let's see that what I am trying to say again. And here we are. So what I am trying to say is, for A1, what we have done is we have taken the node or the vertex 1 as the intermediate vertex. Okay, by intermediate means every time if I have to go from some vertex 2, that is the source, to some vertex 4, that is the destination, I will see if getting from 2 to 4, if there is a valid edge, then I have to see its weight. That is 4 now. And also I have to see a possibility that getting from 2 to 1 and 1 to 4, that is 1 must be the intermediate value. So what is the weight of getting from 2 to 1 and then 1 to 4? So that would be getting from source to intermediate value, that is 2, and then intermediate value to destination, that is 5. So that is 2 plus 5, 7, and getting from here to here is 4. So our if condition is not satisfied. Our if condition, that is this condition here, is not satisfied. So the column, uh, yes, the column of getting from 2 to 4 will not be replaced by 7 but will remain 4. So that is what we have done here. Okay, you can see that getting from 2 to 4 is has an edge, a valid edge, which cost me around 4, but as we have fixed 1 as intermediate value, so I can also check the possibility if getting from either not getting from 2 to 4 directly, I can go via 2 to 1 and then 1 to 4, and if that cost is less than this direct route, I can replace this cost by the indirect route cost. So we'll see one more example, or we can see all the entries of this particular graph. So the first, yes, getting from 2 to 3rd, first entry, let's pick this first entry, getting from 2 to 3rd. So getting from 2 to 3rd, we have no valid edge, as you can see, because the edge is getting from 3rd vertex to 2nd vertex, but not getting from 2nd vertex to 3rd vertex. So we have, so in original graph, that is A naught, I must have put it as infinite, yes, infinite. So in this case, anything that is less than infinity will be replaced here. So this infinity here, which is written in A naught, I can go through 1. So from 2 to 1 and then 1 to 4 and then 4 to 3rd. So 2 plus 5, 7 plus 2, 9. So 9 will be replaced here. Okay, are you getting my point? That the if condition is satisfied in this case, that getting from 2 to 3rd is will cost me actually infinity because there is no valid edge. So I will also see if I can get from 2 to 3rd via the intermediate node, that is 1. So from 2 to 1, 1 to 4 and then 4 to 3rd, it cost me around 9, and 9 is obviously less than infinity, so I'll replace infinity by 9. Okay, so this is the basic rule for, so getting from 2 to 3rd, taking the intermediate route is profitable, and getting from 2 to 4th vertex, getting the direct route is more profitable. So this is what we are trying to say here. Let's get to the 3rd row. So getting from 3rd to 2nd, yani, it means this entry, let's see, from getting 3rd to 2nd is a direct route, and that is 1, and I don't see, it don't seems to me that getting from 3rd to 2 via 1 is possible. Yes, that is not possible because we have no direct connection or any type of connection getting from 3rd to 1st vertex and then getting from 1st to 2nd possible. So we have only one option, we have to put 1 here. So that is what I have done, and this entry getting from 3rd vertex to 4th vertex, getting from 3rd to 4th has no direct route, so it must be infinite in the A naught, but we have alternate route, that is getting from 3rd to 2nd and then 2nd to 1st and then 1st to 4th. Let me again tell you that getting from 3rd to 4th has one more route, that is getting from 3rd to 2nd and 2nd to 4th, but as we have fixed 1 as intermediate value, so our path, our alternate path must pass through 1. So 1 plus 2, 3, 3 plus 5, 8. So 8 is there because 8 is less than infinity. Okay. Now getting to the last row, getting from fourth to second, we have no direct route, so anything getting from fourth to second other than infinite is good. Now, as you can see in this particular case, it's a strange case that getting from fourth to second via the intermediate value is also not possible because we have no path leading from 4 to 1. If I have to reach from fourth to 2, second vertex, 2 vertex, I have to move from fourth to third and then third to second, and which does not involve the intermediate node 1. So in any case, getting from 4 to 2 either directly will cost me infinite value, or getting from intermediate value will also cost me infinite. So the value here will remain infinite. Okay. Now the last one, getting from fourth to third. Getting from fourth to third, as you can see, we have a direct edge which cost me around 2, and getting from fourth to third via the intermediate value will, again, there is no possible way, that means the cost will be infinite, so I will remain with 2, so that is 2. So in this way I have modified my original adjacency graph from A0 to A1, and now A1 is modified, or it actually provides me the shortest path if we take 1 as intermediate value, if possible. Okay. Now in the next step we have to fix the next node, that is node 2, and then node 3rd, and then node 4th. Okay, so let's move ahead. Okay, now here we are for A2. Let me remind you that A2 will work on A1 and not on A0. Okay, so from A1 we'll move on to A2. For A2, as we have done for A1, we have to fix the second row and second column. So basically the rule is, whichever node you will fix as intermediate value, you have to fix the values of that particular row and that particular column. In this case we have fixed the A1. In next case we have fixed the node 2 or vertex 2 as intermediate value. So in that case, second row and second column will be fixed, and all the diagonal elements will also remain fixed. Okay, I think it's clear what is the rule now. For A third, again we have to fix the row third and column third and the diagonal element. For A4 we'll fix this row 4th and this column 4th and all the diagonal elements. So in that way we'll move along. So let's try to input the values. Let me remind you that in this case we have fixed second node or vertex as an intermediate vertex. So first empty entry is getting from first to third. For getting from first to third we have no direct edge, so initially that value must be 0. But now we can calculate. Getting from first to third is getting from first to 4, and getting from 4 to third, and also can we go from first to second, and then second to fourth, and from fourth to third. Now I think this is the only way you can include the intermediate value as an alternate path, because getting from first to third via fourth doesn't include the intermediate value, intermediate node, which is second in this case. So from getting first to second node will cost me around 3, getting from second to fourth will cost me around 4, and getting from 4 to third will cost me around 2. So 4, 7 plus 9. So I have rightly written here 9. Okay. Let me again tell you that getting from 1 to third has one more route, that is from 1 to 4, but 4 to third, but we will not take this route because according to the rules of getting matrix A2, if we have to choose the alternate way of getting from source to destination, then that route must include the intermediate node. And in this case, we don't include the path that doesn't include the intermediate node, that is node number 2. So keep that thing in mind. Okay. Now getting from 1 to 4, getting from 1 to 4, we have a direct edge which weighs around 5, and getting from 1 to 4, we have alternate route which includes the intermediate value, that is getting from 1 to 2 cost me around 3, and then 2 to 4 will cost me around 4. The total will be 7, which is actually more than 5. So I will stay with 5. So 5 will be there. There it is. Now the second row is fixed, so we'll not touch that. Now getting from third to 1, getting from third to 1, we have no direct edge, so the initial value must be infinity. Now via intermediate value we can get there. So getting from 3 to 2, I will have to bear the cost equal to 1, and getting from 2 to 1 I have to bear the cost 2. So total will be 3. So I will insert 3 here, as you can see here. And now for this entry, getting from third to fourth, let us see. Getting from third to fourth, we have no direct value, no direct edge. So initial value must be infinite. Now we have an alternate route by intermediate value, that is getting from third to second and then second to fourth, which will cost me around 5. So I have rightly written here 5. Now in the fourth row, I have two empty spaces. First is getting from fourth to 1. Getting from fourth to 1, we have no direct edge. I can use the intermediate value, that is getting from fourth to third, then third to second, and then from second to first. Okay. Now it will cost me around 2 plus 1 plus 2, 5. I don't know why I have written infinite here. It must be 5 here. You can correct that. It must be 5. Okay. Now next is empty space. Getting from 4 to third is again will cost me around 2. I have rightly written here 2. So that concludes my A2 matrix. Now we'll go from A2 to A third. This is my A third. For that I have fixed the third row and third column and all the diagonal elements. Again we'll start calculating each of the empty spaces. So as you can see, getting from 1 to 2, from 1 to 2 we have a direct edge with a cost third, so I will replace third. Let me say that again, we have intermediate value fixed as third in this case. Okay, so getting from 1 to 2 via third is costly, that is 5 plus 2 7 plus 1 8, while getting directly from 1 to 2 cost me around 3. Okay, so the value will remain 3 here. Now getting from 1 to 4, we have a direct edge. Okay, and there is, I think, no way I can get from 1 to 4 via 3, so that value must be infinite. Now 5 is obviously less than infinite, so I will stick with value 5 here. Now getting from vertex number 2 to vertex number 1. From 2 to 1 I have a direct edge which cost me around 2, and I think there is no way I can get from node number 2 to 1 via routing around 3. So I'll stick with this value 2 here. And the last value, from getting 2 to 4. Getting from 2 to 4 I have a direct edge that cost me around 4, and if I have to go through the edge, if I have to go through the vertex third or node third, I think there is no way. So that route, getting from 2 to 3 and then 4, will cost me around infinite, and definitely getting from 2 to directly 4 will cost me around 4. So I will stick with 4 and leave out the infinite value. That is what I have written. So in that way, you can complete this graph here. You can complete the A3 here by calculating deciding if getting the direct route is profitable or getting the alternate route is profitable. Okay. And in the last step, I will move on from matrix A third to A fourth. This time I will fix fourth row and fourth column. And then when we'll calculate this particular matrix, this matrix will provide the shortest path for each vertex getting to every other vertex. So let me remind you, the A4 vertex has evolved from A0 to A1, then A1 to A2, then A2 to A3rd, and then A3rd to A4th. So it encapsulates all the good elements of all those adjacency matrix. Okay. Okay. Now this A4 matrix is does actually include all the shortest paths getting from each node to each and every node. So getting from 2 to 1, 2, 3, and 4, the cost will be around 2, 0, and 6 and 4. Now these are the minimum cost that you can have. So this is the best possibility you have for getting from node 2 to each and every other node. Okay, so I have stuck to A4 only because I have only 4 nodes in this particular graph. You will keep on doing this procedure for as number of nodes as you have. Each time you will fix one of the node or one of the vertex as the intermediate node, and then you will fix the that particular row and column, and in that way you will calculate the matrix which will give you the shortest path of getting from each node to each every other node, keeping the intermediate node as the fixed node as your intermediate node. And at the end of the procedure, when you will have gone through each and every vertex of the graph, the end matrix will give you the optimal solution, that is the shortest path of getting from each node to every other node. Okay, so that is the Warshall's Floyd algorithm for you for traversing through one node or one vertex to every other vertex in a directed graph. So I will end this lecture and this unit now, and tomorrow we'll start with some new unit. Okay, thank you.